Jason MacDowell from GE, who's on a 2-year assignment with us at ESIG. So I'm very pleased to welcome Jason to chair this session. Jason.
Thank you, Charlie. Good morning, everyone. And as Charlie said, and in the spirit of what we had heard yesterday from Ong, I'm Nick Miller, stunt double for today. And really wish he could be here, and regrettably, maybe we can get him to come and chair the next session next time we see him. So today we're going to focus on subjects related to some of the topics we talked about yesterday on stability and technology integration. And a lot of the subjects you're going to hear today are really being worked on and are a focus of our reliability working group. So those members that would like to join the reliability working group tomorrow, we're going to dive deeper into some of these subjects that you're going to hear about today. Just as we've been doing so far, I'll introduce the presenters. And if we have any quick clarifying questions, we'll take them after each presentation, but we'd like to save a good dialogue and discussion for more in-depth questions at the end. So with that, I'd like to introduce our first speaker, Dr. Julia Matevosyan. Julia is going to talk about a comparison of current grid forming specifications. And Julia is ESIG's chief engineer and has more than 20 years experience in the power industry. Prior to ESIG, she was the lead planning engineer for ERCOT. With her time at ERCOT, she worked on adequacy of system inertial response, flexibility, frequency control, and performance related issues relative to high penetration of inverter-based resources, and was a key player in developing the ancillary services market in ERCOT. So please welcome Julia.
All right. Good morning, everyone. So I'll start the timer. Yes. I'll talk about comparison of grid forming specifications. So that these were coming in the past couple of years. So before I even go ahead and get started, I wanted to go into a definition of grid forming. So grid forming is a buzzword on its own. But then also I think is what becomes the buzz question is, what do you mean by grid forming? And so before we start talking about what a specification for grid forming, I wanted to bring up this definition that we have developed in our grid forming technology and energy systems integration report that came out in March this year from ESIG, and I have it linked up in the slide below. According to that definition, the primary objective of grid forming controls is to maintain internal voltage phasor. When grid forming controls are applied in bulk power system connected inverter-based resource, the voltage phasor is held constant in subtransient and transient timeframes. And this allows inverter-based resource to immediately respond to changes in external system and provide stability and controls during challenging network conditions. This phasor must be controlled to maintain synchronism with other devices and control active and reactive power output to support the grid. And when grid forming controls are applied in non-bulk power system connected inverter-based resource, for example, in case of black start or microgrids, this synchronization functionality is removed or limited, and voltage phasor may be held relatively constant over time, and it allows a grid forming plan to set electric frequency of electric island. There are many variations of grid forming controls and also of grid following controls, and both are subject to physical equipment constraints. So this is something to keep in mind. So I was talking to people here during the workshop, and so like the first thing that people bring up that there is no common understanding of what grid forming means, and so I think like looking at requirements that I've analyzed, I think there is a core agreement of what grid forming is, and core agreement is that it's holding voltage in subtransient transient time frame, inverter-based resources holding voltage constant and then injecting current depending on what's happening on the system. And I think it's not so dissimilar to if you generators also differ one from another depending on what kind of functionality is there. So at the core, synchronous generator is a machine synchronized with the grid rotating machine, but then you may have governor response, you may have AVR or not have AVR, you may or may not have power system stabilizer. So similarly, I think grid forming at the core is, holding voltage constant during disturbances, but then depending on what other functionalities it can provide, this is where the difference is. So I think maybe we should stop asking question, what is grid forming, but rather ask question, what grid forming functionalities are there? What functionalities are you talking about? I have a grid following definition there just for completeness that came out from that same report. So I wanted just to have it there in the slide deck. So talking about grid forming specification landscape. So these are kind of main specifications or specification-like documents that you can find out there. So EU-funded Migrate project proposed really high-level, I think 5 or 6 functionalities for grid forming in 2019. Then there was a group at ENSOE, which is Association of System Operators in Europe. They also identified 7 properties of grid forming plant. And again, those were relatively high-level functionalities. And then there is VDE FFN guideline for grid forming behavior in HVDC systems and power plant modules. So this one is more, it's a bit different. It doesn't define functionalities, but rather it's saying how do you test for different grid forming functionalities. So it's describing performance that you expect in tests for grid forming. Hawaii Electric Company now is requesting grid forming functionalities from all proposed projects that include battery storage. So basically either storage projects or hybrid projects. And they have high-level functional requirements. Again, there is a number of functions that are listed, but also they are asking for detailed models, and then in tests on these models, they are verifying if these functionalities are available and how the model is behaving. Then National Electricity System Operator in Great Britain finalized the grid code change GC 137, and this is, as far as I'm aware, the first in the world non-mandatory grid forming specification included in the grid code of any power system. So that was finalized in the beginning of this year. EU-funded Osmos project, which was a continuation of Migrate project, among other things, defined grid forming capability and new services that potentially can be provided by grid forming inverters as synchronous generators are retiring or being not committed in the unit commitment. DOE funded project Unify that started about a year ago, among other things, again, is focusing on specifications of grid forming technologies. Currently, there is a draft being worked on functional requirements and performance criteria for grid forming inverter-based resources. At the same time, I'm chairing inverter-based resource performance subcommittee at NERC. And so we are getting questions from utilities, especially vertically integrated utilities who maybe have more decision power to go and test it out. And so they're asking, okay, so you're talking about this grid forming, is it commercially available and what does it mean? What should I go and procure to get grid forming on my grid? And so there is this initiative going on in NERC IBR IRPS to define grid forming capability in BPS connected battery storage systems. So the idea there is to explain with this high level functionalities that are out there in specifications, what does it actually mean, and what to go for, what to ask for. And then the last but not least, Australian energy market operator currently is also working on a draft of voluntary specifications for grid forming. And it's an ongoing work. There is no published document out there yet. So in the rest of my presentation, I'll focus on some of these documents that are listed, not all of them, just some of them either that have more details in them or I found interesting for one way or another. So National Grid ESO grid code change that I mentioned was approved in the beginning of this year. It has non-mandatory set of technical specifications. What is interesting about it is, first of all, that it's non-mandatory. So the idea is it will be procured as a service and paid for. Currently, it's already being procured through a number of tenders where National Grid is coming out and asking for certain amounts of short circuit strengths or inertia, so short circuit strengths in local area, or inertia system-wide, and then inverter-based resources that are offering into this tender, they have to comply with this new requirements in the last tender phase, in the one that's ongoing right now. So the previous stage just concluded, and 5 grid forming batteries were already procured and awarded as a part of this tender. So this is already happening. So I have a list of one more thing to add. These requirements are still kind of not very detailed. They are currently working on best practice guide, which is kind of like application guide to explain what some of these requirements mean and how to test for it in using models and also using actual measurements. And also another thing, which escapes me right now. Oh yeah, another thing is that some of the requirements, it doesn't prescribe the amount of service that you have to provide, but you have to declare it. So say amount of inertia or phase jump power that you provide, you have to say how much you have, not, there is no prescription of how much you should have, which I think is a good thing, provides a lot of flexibility. So some of the basic functions that they require is phase jump active power, real inertia power. So both of these are in response to disturbance on the grid, amount of active power that is expected almost instantaneously from a grid forming resource. Rate of change of frequency response power that combines some of these responses together with controlled frequency response, which is more similar to how grid following inverter can respond as well. Damping active power, voltage jump, reactive power, which is again almost instantaneous reactive power injection, fast fault current injection. And then there are these 3 functionalities in green that are control based, and I colored them green because I think the grid following inverters might as well are also capable of providing it. So I'm not really sure why this functionalities are called out in grid forming specifically. It would have been a grid following capability. One thing to add that in all of the specifications that are out there, grid forming capabilities are on top of the requirements that already apply to grid following inverters. So everything that's already there and been developed, say in IEEE 2800 was mentioned yesterday, in this type of specifications for grid following inverters, it also applies to grid forming unless there is some kind of conflict between grid forming capability and what's in the requirements for grid following inverters. So apart from this kind of specifications that are kind of for the grid, they also have some requirements that are for right through. So for example, there is a 60-degree phase jump angle withstand capability requirement. And there is also a minimum phase jump angle limit, which prescribes for what phase jump angle the inverter shouldn't hit its equipment limit. Right, going to Hawaii. Hawaii has a number of small island systems. By 2023, some of these islands may be seeing 100% renewable penetration. Also, what's specific about the system is that 50 to 70% of inverter-based resources on those systems are distributed resources. So basically, these systems will need to be relying on grid forming inverters to maintain grid frequency and prevent blackouts going forward. The studies for 2023 for islands of Oahu and Maui already showing that studies, that they're showing instability if only grid following inverters are there. So initially they came out with just a high level definition. I will not read it out, it's on the slide there, of what grid forming inverter means and supposed to do. And they said that every new storage resource or hybrid resource that will be procured has to comply with this definition. This is very high level. There is no, specifications of functionalities. And so to clarify it more, there was a number of tests that were applied to prospective generator models. Then there was a more detailed AMT study conducted on some of the Hawaii systems, and they came up with a bit more detailed requirements for what grid forming actually supposed to do, and came out with this however many 8 functionalities. And so these are high level, kind of similar themes to what you've seen for national grid, and to operate in a stable manner in low short circuit strength system, set internal voltage waveform reference, and either synchronize with the rest of resources on the grid or operate as an island, like just operate a grid that has this one grid forming inverter there. Response to changes to system frequency and voltage. So that's similar to instantaneous active and reactive power injection in response to different disturbances, provide damping. If last synchronous generator is lost, it has to continue operating in a stable manner and synchronizing with other grid forming, grid following resources on the grid, or operate as a part of the system as an island. Be able to transition from electrical island to grid connected and back, cancel low order harmonics, and provide black start capability if applicable. So not all of these resources are expected to provide black start capability, but only some. Similarly, how currently synchronous generators, not all of them are black start capable, but only a subset of those. Jumping to EU-funded project Osmos, they also have specifications for grid forming, just as a on a plant level. But I think what's interesting here is that they identified what they call synchronization services. So some of the services that are currently being provided by synchronous generators and will no longer be there when synchronous generators retire. And so these services can be provided by grid forming inverters and remaining synchronous generators. So this is this gray area on the left-hand side figure. Everything on the right-hand side is currently being provided either by synchronous generators or grid following inverters, and these are all frequency services. And then they identified the stability synchronization services that grid forming inverters can provide. And this again includes synchronizing active power, which is what was called phase jump power in national grid requirements, inertial response, system strengths, and fault current. I think what's interesting here is that they identified that grid forming inverters can be separated in 4 different groups depending on capability. So this is going back to the definition, what's grid forming, and can a core grid forming, can it be defined, and then everything else is kind of additional functionality that's added on top and just defines hardware that you have. And so this type 1 grid forming is a basic grid forming. GE also calls it core grid forming, and that's the one that can ensure standalone operation, provide system strengths, fault current within rating, and operate in a wide range of short circuit ratio. And this doesn't require any extra hardware. In a battery is a change of controls only. And it becomes necessary if you're seeing local system strengths issues. Then type 2 is where you add synchronizing power. So this is when you start seeing that local system inertia is declining and requires a little bit of storage energy buffer, which is less than a second. And then all fast frequency response, primary frequency response can take over from other resources. Type 3 is type 2 plus adding inertial response. So this is when you're seeing global inertia decline in the system level. And then type 4 is when higher fault current level needed for protection. And so this is requiring either oversizing of inverters, or maybe that's where synchronous machines still are really good to provide, because they can do fault currents way over the rating of the machine. Just briefly to mention Unify, as I said, this is still working draft. Overall, looking at it, the common themes are similar there. It's just functions are called slightly differently. It splits between the normal grid operating conditions and disturbance conditions, and so lists these functionalities, depending on this category. Right. So kind of looking at all of these requirements, yes, they all call things differently. They all go to different levels of detail. But if you look across and you kind of understand what this functionality is about, they're relatively the same. So you look across the requirements that I just mentioned, and in green, it's all yes. And so this high level is required there. It may be, has more details or less details in it. And so they all require some kind of response to phase jump, inertial or immediate active power injection. System strengths is called in some requirements, and others is immediate reactive power injection. Fast fall current. I couldn't find in the VDE clear requirement for or how the fast fault current injection is tested, but I might have missed it. So I just said to be confirmed there. And again, the low short circuit strengths operation is everywhere. Active reactive power sharing is either implicitly called upon, or it's like if you're reading through island operation and how it is defined, you understand that active reactive power sharing is required there. Damping in Osmos report, that's because French system operator already requires damping from grid following inverters. So they say that maybe additional damping capabilities may be required from grid forming, but they haven't quite defined it. And then countering harmonics is not defined in GB requirement and in Osmos is because they, again, both of them recognize that it's already required from grid following. And they need to investigate if additional capabilities needed there. And Black Start, commonly across all requirements, it's if applicable. So they all recognize that not all grid forming resources will be required to be Black Start capable. So I just call this functionalities here. I won't repeat it, just to show that these are common themes across all of the requirements. It's just the question of how, devil is in detail, but functionalities, I think all of them agree on what the functionalities that we seek are. So just to conclude, this is still a new topic. We are developing specifications at the same time as controls are being developed by manufacturers, and a still active area of research as well. All specifications are similar in terms of functionalities that they're looking for, with main differences being around level of details and also if requirements are specifically called out or are implicit in some other requirements. So for example, like active power sharing. Right. Some of the cases of high-level requirements are accompanied with more detailed description of tests or what to look for in tests. I think this is actually a good thing at this stage because the technology is still developing. So it's good to not to over prescribe it before we know what we actually need and what we're looking for. So maybe one recommendation, it's a personal recommendation from this analysis, is that it's good to go for higher level functional specifications with more detailed descriptions of tests and performance that we're looking for. And some functionalities can be implemented in grid following inverters, and therefore maybe we shouldn't call upon those in grid forming specifications and just cover sheet say that grid forming inverters have also to comply with existing grid following interconnection requirements. And so before I conclude, before I finish, I wanted to bring up to your attention the high share of IBR task force that we have currently at ESIG. And I listed some activities that we currently have going on. We are working on a paper that started with Andrew Isaacs's phrase, just do it, when we were in the grid forming workshop. Basically, the idea was that grid forming is a low-hanging fruit in batteries. And while Hawaii system depends on having grid forming for their reliability already now, other bigger systems actually have time to test it out and try it. And so just do it and go ahead and do some tests, and maybe you'll change requirements over time, but pilots are encouraged. And then the second paper is on grid forming landscape. So we are going to just kind of write up what is happening in the world with regards to grid forming pilot specifications, and any kind of new tests that are happening or new grid forming controls. So just cover the research and industry landscape. Next paper is on what grid forming specifications mean. So we'll take this set of specifications that I just described and try to practically practically describe what you're looking for in tests when you're trying to provide this grid is on new services with high shares of inverter-based resources. And there we are actually planning to do a test case study, potentially using ERCOT system. And then one project group that Nick leads is on stability assessment methods. And so this one is looking at how do you assess stability in high IBR system and primarily currently focusing on oscillations analysis. So with that, thank you very much. Yes.
Great. Thanks, Julia. Okay, so let's move on. I noticed that Nick was feeling well enough to be able to join us in remote in. So Nick, if you have any questions or anything, please feel free to just chime in. I'd like to introduce our next speaker, Dr. Babak Badrzadeh from Australia, all the way in. So thank you for joining us. I know it's might be a little bit hard to be speaking at your night at the moment, but Babak is going to talk about assessment of grid following and grid forming inverter-based resources and synchronous condensers in Australia. And he's currently the technical director of power systems with Aurecon based in Melbourne, and is also an adjunct professor with Monash University and a distinguished lecturer with IEEE PES. His current areas of focus include power system modeling and analysis, technical and regulatory developments, and power system technologies and integration. So please help me welcome Babak.
Okay, thank you very much, Jason, for introduction. Good morning, everyone, and really very pleased to be here. So what I'm actually going to do for today's presentation, I'm actually trying to share some of the recent experiences that we have had, and they are unrelated, so I'm just trying to make best use of these 15 minutes that I have available, and it's sort of complementary to the second presentation that I'll be making. I may be skipping some of the points in this presentation, but hopefully that make it clearer when I finish the second presentation in session 7, basically. And I am not providing a like-for-like comparison between grid following inverters and grid forming inverters and synchronous condensers, but it's just sharing some of the notable experiences, at least for myself and the work that we have been doing in Australia. And hopefully it's something that you can use and learn something from and apply it in the work that some of you do day-to-day basis in United States, basically. So starting from grid following inverters, the first issue I wanted to highlight is the reactive current injection during the fault. And for those of you that are involved one way or the other in grid connection studies, you know that there are requirements, including in IEEE 2800 that we learned yesterday, that essentially require a prescribed level of reactive current injection or absorption during fault condition. And typically, it's assume a linearized response that some levels of, say, 2 to 4% of reactive current injection as function of the voltage deep in the network. And what I'm actually presenting in the next 3 or 4 slides, just some of the challenges, and these are everything that I'm presenting vendor specific and site specific models in EMT. So these are all real, basically results, real project is nothing basically made up, but some interesting results and what we can learn from. Okay, the first thing, like I said, is that when a fault happens, what is the overarching objective? What we really want to do, and what is expected from an IBR or even a synchronous generators? If fault happens, basically, the voltage goes low, how you can aid the recovery of network voltages, and what matters really? During the fault, the voltage depressed, so you have no opportunity to raise that up. Basically, that's primarily driven by RLC, basically impedances. Just before the fault clear and at the fault clearance, if an IBR can inject some levels of reactive current injection, it means that that can assist the recovery of network voltages faster, especially as synchronous generators are being very rapidly withdrawn from the power system. With that note, what it means is that once a fault occurs, say a cycle or cycle and half, including measurement delays and everything, you expect to start injecting some reactive current and basically hold that response as far as possible. What is shown here is a response to a two-phase to ground unbalanced fault. It's a fairly severe fault, as you can see from the first trace. And as you can see, in the initial period, the IBR provided a positive response, but it cannot hold actually this response, and it's very variable, which I will discuss the variability element in the next slide. What I wanted to highlight here is exactly where I have put the arrow, is that you can see that just moments before or millisecond before the fault clear, the reactive current injection is lower than when the fault initiated, basically. And that might cast doubt as to whether this particular IBR providing a useful contribution or any contribution to the network. Is it perhaps even adversely impacting? And if not, what else are we missing? So should we be looking at something else? Should we be changing the frame of reference perhaps? And let's see what else we learn. Okay, I briefly discussed about the variability element in the previous slide. Similar fault, again, two-phase to ground fault. With three-phase fault, typically we don't have these problems, so there's no problem. Let's not spend time in it. But the bad news is that all practical fault in power system are unbalanced faults, basically. Now, this is, again, all these results are real responses, basically. You can see the variability even clearer here. Is that fault occurs, and initially always there's a good initial response, but it cannot be maintained for a variety of reasons, which I will cover in the 4 slides that I have in this particular topic. The main point I want to convey from here, because I've already shown you the variability element, is that even assume that in this case, the response is not lower than when it started, basically. But the challenge here is that what point should I be looking at? Because if I'm looking at 5 milliseconds before or after, it might be giving me a very, very different result. So how can I use a fairly linear response, which is prescribed, whether it's in Australia or Germany or Europe or US, it's all following the same principles. How can I make sense of it? If I'm looking at 5 milliseconds after, it could be 100% different. Is it success or failure? How do I know? Okay, the third issue I wanted to raise here, again, similar fault, two-phase to ground fault. So in this case, the response doesn't go negative. It definitely follows basically a positive trend. The middle graph, which is a positive sequence response. But then we basically plotted the negative sequence response, which is the bottom graph. And you can see that in this case, it goes negative and it stays negative. Again, it might give the impression that this is an sort of unexpected or unacceptable response, basically, because a fault happened, you expect to go upwards. It's not an over voltage. And the response clearly goes downward, basically, as far as negative sequence current is concerned. But then what is happening exactly? So this is for a type 3 wind turbine that has a loose but important coupling to the grid that it's which is basically a sink for negative sequence current. The synchronous generator is always an induction machine that is used in a type 3 machine. It's fairly similar. The initial behavior is driven by machine and flux dynamics, basically, and you cannot simply do anything about it. And this is inherent response. So meaning that the current that has to be absorbed, it's first taken, and then some of the current would also need to go to the active component, active current component, and how much current is left to play with as far as the reactive current is concerned. And again, I discussed this in greater detail in the second presentation in terms of allocation of current between different components. But the key point I wanted to highlight is the contribution of negative sequence that here is going downward. And if I was to look into positive sequence only, it gives me part of the answer, but it underappreciates the total response that the basically generator has provided. So now what we discussed here is basically the issues where the non-linearity of the response, there's huge variability and potentially reactive current sometimes being in the negative region, and then how to account for negative sequence current. But the main thing is that how we can define success based on such a non-linear response. And then we started to think what else we can use as a frame of reference, not necessarily requiring a different response, but using a better, more reliable, more meaningful measure of success, basically. And with that in mind, again, another two-phase to ground fault, they're fairly similar if they're not identical. Most of them voltage drops to around 20%. And what we've done in this simulation graph is that we compare the positive sequence reactive current, total reactive current, whether including both negative and positive sequence current would fix the problem perhaps, or are we missing something else? And then last but not the least, the total current, which has shown in the blue color. And as you can see with the total fault current, it's fairly constant. Initially some wobbles, but it's significantly more reliable compared to both the positive sequence reactive current and total reactive current. And that basically, and this is just as much as I can discuss here, basically with minutes that I have available, but it has given us a caution that maybe we are looking at the wrong metric. Should we be using the total current, which accounts for positive sequence, negative sequence, active current, and reactive current? There is no unintentional prioritization is required in this instance, basically. So this was the key message I wanted to highlight. Are we using the right metric to assess the success for reactive current injection or for positive contribution of an IBR during fault condition? The second experience is for grid forming inverter challenge. To summarize, and we have quite a few actually practical projects, large sizes, 50 megawatt to 600 megawatt grid forming battery projects. The three main challenges I wanted to put out there. The first one was the lack or immaturity of the phasor domain models. And this might look counterintuitive. Typically, people think that EMT models are the harder ones, but EMT models these days are essentially one-to-one representation of the source code. We really don't need to do much, whereas the positive sequence or any basically sequence phasor domain models need to be still developed by humans. And these models are not mature at all. I can basically tell you only one or two or three basically suppliers had good enough phasor domain models for grid forming batteries. The second one is the lack of technical performance requirement, or maybe again looking at the wrong angle. I will present you again a real life experience from another project that I'll be showing in the next couple of slides. And then this third one, I think I briefly discussed even for grid following inverters. And for grid forming inverters, I mentioned, and I come back to this again in my second presentation. Sure. Second presentation, that how we prioritize what is needed by the power system, depending on where you connect it. You cannot achieve all functions that you have in mind, how you can prioritize on a case-by-case basis. And typically, when we're talking about grid forming and grid following inverters, this is an exaggerated, basically, way of thinking. But a lot of people that I have been speaking have this impression that essentially grid forming inverters are problem-free, and all the bads are with grid following inverters. So what I was presenting maybe in previous sets of slides, people might say that it's not surprising, all bads with grid following inverters and all the goods with grid forming inverters. Is that true though? That's not what we are seeing really. The differences are not really as black or white as you might be thinking. They're fairly close. Surely grid forming inverter more superior. And here I put 4 points that I thought I'd like to demystify basically with regard to performance of grid forming inverters. What we have seen that they don't have any susceptibility or instability mechanisms. I'll show you in basically the next set of a slide. And they can resolve all these problems in basically power system to which they are connected. That's not true again. I show you another set of slides. And whether they substitute grid following inverters in midterm is speculative. We can't say that. I don't expect that to happen, but again, we will learn that. And whether or not we can operate system without any synchronous machines and completely with grid forming and grid following inverters. Again, the answer to that is not known. So let me share you again practical experience with grid forming inverters. It's based on virtual synchronous machine. It's a very big part of network. SCR at connection point 2 at the inverter terminal is marginally above 1. And there are other inverter-based resources. So this SCR of 2 that I'm quoting is on a single, basically, unit. And this is this way of implementing swing equation. Again, this is not surprising. And the problem that I'm starting here and building up in next to a slide is whether virtual inertia is something useful for all instances. Other problems I've mentioned, and especially the conflict between virtual inertia and the frequency response, I build on that in the second presentation. I actually skip. Now, bearing in mind that this connection point has a SCR of around 2, what we have done, and in this case, no fault is happening. So it's just a frequency event. And because of the virtual inertia, if the frequency goes up, active power, you want to basically take it down. And with battery, you have all the means to do that. What is happening here is that the active and reactive power are not decoupled anymore. It's a very big connection. They fully coupled indeed. And by virtue of moving active power and because frequency changes, what is happening is causes voltage collapse and it triggers LVRT basically on the grid forming inverter, and there is no fault basically here. So you can see that this is clearly an unacceptable response. The other point to highlight is that maybe impression that we have typically that the bigger a response you provide, the better it would be. And what I'm trying to highlight here is that we have varied actually the key 2 parameters. One is the inertia constant, the other is damping coefficient. And you can see that as these numbers increases, the level of oscillations and also the magnitude of the response also changes, which is not, again, something that we want to have in a big part of the network. Now, basically 1 minute would be sufficient. I have actually presented the longer presentation twice at ESIG events on synchronous condensers. I'm not spending much time in it. So one thing I want to highlight is that what is happening or what has been there in Australia, most of this synchron has been driven by owners of inverter-based resources. To date, it's not happening anymore. Only there is one synchron currently, or 1 set or 4 sets actually, that are basically introduced by the network owner, which is exactly what I'm showing here. I witnessed these synchrons 4 months ago, and that's where the photo is taken. And what we have learned about synchronous condensers, obviously they're much simpler, so we cannot deny that compared to any inverter-based resource. Much more known, so easier to model, easier to understand. With that in mind, we have not had a single synchron being proposed and approved in past 12 months. And maybe there's a few reasons. Partly is the becoming more expensive than grid forming inverters, longer construction time. And one thing to highlight here, which is different to where you basically live in the United States. In 2016, we had a basic blackout, which basically changed the scene for us. So the risk-taking appetite in Australia is much greater in basically compared to US to basically try something new. Grid forming inverters are happening. They are not like a laboratory level. And because of all combination of these things, we're not really seeing much of synchronous condensers. And the other thing is that we might think these are highly reliable equipment. I'm not saying they're unreliable, but we have had multiple failure events and essentially single point of failure. If a synchron of say 200 megawatt is gone, then game is over, and take many months basically to fix that. Despite that, I think it still is a good tool in the toolbox, especially with the supply chain issues that we are seeing. We are all competing in Australia and Europe and US to get basically share of this very limited and scarce supply chain, especially with the situation on lithium ion batteries. So I'm not ruling out synchronous condensers by any means, but we are not really seeing much of it happening. One thing I can tell you as a fact, basically, because of regulatory development, moving forward, the IBR owners won't be connecting these synchronous condensers. It would be primarily orchestrated by the network owners. And that concludes my presentation. Thank you.
Difference. Thanks.
Great. Thank you, Julia. Thank you, Babak. It's really great to hear from you. I'd like to call up our next speaker, Dr. Lingling Fan. Lingling is going to talk about identification of causes of various grid oscillations. And this subject, we're also going to be working more deeply on. It's a task force. You heard from Julia that Nick is leading in our reliability working group, and really looking forward to hearing more about the oscillation detection. And so Lingling is a full professor at the University of South Florida. Prior to joining academia, she's been with MISO for 6 years after receiving her PhD degree in electrical engineering from West Virginia University. And she was elected to IEEE Fellow for her contributions to stability and control of inverter-based resources. So please help me warmly welcome Lingling.
Good morning. Thanks everybody for this great opportunity to present this research, replication and identification of causes of grid oscillations. So I want to share with the audience the 3 critical components of replication and identification. And let's move on. So these are the 3 components I put here, which is data collecting. For any real world dynamic phenomena, you want to comprehensive data collecting. And then hands-on computing, which include EMT simulation, hardware experiments. Furthermore, this is another critical component, which is called analysis, including reasoning, mathematical modeling, kind of control theory application. And with all 3 components, I think we can have those kind of dot connection, make some initial guess, and sort of like keep doing the investigation and to couple of iterations, and finally to find out, oh, this is what's happening. So the material of this presentation will be based on one task force report called TR80. This is on wind farm oscillations, and a couple of task force papers. These 2 are already in IEEE Explore, and then the 2 research papers from our group, one on analysis, one on experiments, hardware experiments. So I want to emphasize this data collection point because it's very important. For example, the left part, this is a figure from the TR80. In entire chapter 2, we have all these people talking about events. What are those events? What do they look like? What the generator look like? What does the grid look like? And the field measurements. So therefore, based on those things, we can roughly categorize. For example, there's this SSR event, mainly related to the type 3 generator and wind turbine. And then you have to have these radio connection with series capacitor. So that's the first category called a series capacitor, SSO. And then there's another category which is related to mainly type 4 wind and the weak grid. There's no series compensation, but the grid strength is pretty weak. So we call it weak grid SSO. So that 6 events we can roughly categorize into 2 categories. And furthermore, field measurements, very, very important. So in the right side, you can see 19 events have been collected from the task force paper. And I want to point out one of the event, which is called Hydro 1 20 Hertz, comparison with Dominion Energy's 22 Hertz oscillation. They all look similar because they have same frequency if you look at the voltage measurement, the RMS value, or maybe real power. But they are very different because the Hydro 1, if we look at phase current, the instantaneous current, it has a majority, the dominant frequency is 80 Hertz, not 80 Hertz and 40 Hertz. However, in the Dominion case, this is called sideband oscillations. 2 sides, you can see the phase current. There are 40 Hertz, there are 80 Hertz, something like this, or 38 Hertz and 82 Hertz. So these 2 are actually different. So moving on, if we have this data collecting thoroughly conducted, I think the next case is the hand computing or set up the test bed trying to replicate initial replication. So here, what I just talk about a little bit of the fundamentals of the converter control. I think everybody is pretty familiar with this grid following control has 3 components, which is very fast current control. And outer loop, they have this vector control called decoupled real power, reactive power following, slightly slower. And then they have this phase locked loop, which is conducting synchronization. So this material has been published in 2010 textbook already. Moving on that, once we put IBR into the grid, you have to put a lot of plant control, which has not been mentioned in the textbook yet. So here, in fact, we can see that there's a hybrid power plant. It consists of 1 PV, 1 battery. And at the plant level, there's a control, which measures the frequency and send out the real power order to both PV and battery. And it also measures the voltage at the point of interconnection and send out the reactive power order to both converters. Right. So this is the hybrid power plant level. So combining all together, the initial or the fundamentals we need to understand there's this bandwidth issue or difference in the bandwidth. For example, if we see some dynamics like 1000 Hertz, probably it is PWM switching combined with maybe filter or this kind of hardware stuff. And then at 100 Hertz level, you can guess probably it is the inner current control related issue. At 10 Hertz level above, then you can guess probably it's PLL or auto control or auto power or voltage control. And then very low frequency, people can guess that is probably plant level control. So so that's what's happening in the fundamental. And also in the fundamental is that basically we can build any kind of model if we know what is this and play with the parameters and create lots of different oscillations. For example, in this chart, I have provided various causes of weak grid oscillations. It can be roughly said has 3 different types. This is all based on simulation, like a dynamic voltage stability issue, PLL related issue, or slowing the current control issue. And all these, again, you can classify them to be various of issues. For example, even in the dynamic voltage issue, you can see it is because outer loop or because of plant level that they are different. And then it can also be because of the PLL and the interaction with the fast power control. In the PLL level, it can be the PLL insufficient damping because you put a lot of filter to filter out the negative because interaction with shunt capacitor. And if the inner current control is not designed ideally, you can again see something happening. So yeah, so it's not that simple that we can say, what is this? This is based on simulation. Now with that, the most difficult part, I think, in the real world dynamic analysis, besides this data collecting, and you have EMT, is the matching part. Because you really cannot directly connect dots easily. So this part I put it as an emphasis is this is about reasoning, about analysis, mathematical model building, iteration. And it can take years of thinking to finally figure out what is happening. So in the next couple of slides, I'd like to give an example regarding the weak grid voltage stability related oscillations. So these 4 events are taken out from the task force paper reference 1, which is in the Explore 19 events. So number 3, number 4, number 5, number 6, they share very similar feature. This feature is that oscillations occur about less than 10 Hertz, sometimes a little bit of 13 Hertz, but mainly it is 3 Hertz, 4 Hertz. When the line is tripping or when the wind power, solar power ramping up, oscillation happen. And then afterwards, you can tune controller, which is called a voltage control, especially the number 4 event is the Texas event, based on the Texas reference, the ERCOT paper. Voltage control can be tuned down to make the oscillation go away. So The initial guess is this is typical voltage stability issue because voltage stability is the grid become weak, power ramping up, then you see that the voltage will collapse. The difference is oscillation will appear instead of directly collapse. So with our knowledge regarding the converter, we can set up a test bed. And here in our lab, we set up this hardware demonstration, basically have an inverter, three-phase voltage source inverter, connect to the grid. Everything is hardware, and you can tune the grid, make the parameter large. So the SCR, short circuit ratio, is about 2 in this case. So then we keep pushing power to the grid from the inverter. And you can see that in the left figure, the first figure, the inverter is at PQ control mode, which is regulate real power, regulate reactive power. There's no plant level control. And the voltage will collapse at a certain level when the P is ramping up. And then the second one, then really you show the oscillation because we switch the reactive power control to the voltage control, oscillation happen. And then the third one, we can again play with parameter and see that even PQ control, when we make a P control very fast, oscillation can happen. So if we look at second one, we think, okay, we sort of like got it. It's about 3 Hz oscillation, it's weak grid and power ramping up. It is there. So we are pretty happy with that. However, there is one thing that we should say exception. The exception is that the fast voltage control in the previous cases are all behave better. They will make system good. So for example, in this case, in the PV control case, if we make the voltage controller faster, oscillation will go away. So now this component is very different from the real world observation because the real world observation says fast control is bad. We tune down the controller and make it bad. And I confirmed with ERCOT people and they told me, yeah, that's what I do. So we did further study and did this theoretical analysis. Everything told us that fast control is good. And even like a couple of years ago, I checked the Julia and Babak paper, basically also says, if you do fast terminal voltage control, you got almost like grid forming behavior, which is good for stability. So then this is the big question, why? How do we understand this real world phenomenon? Because we are not 100% there. Yeah. So the next thing is finally we find out that the 2 voltage controls are different. In our case, it is the inverter level control. In the ERCOT case, it is plant level control. The one difference is their delay. In the plant level control, you cannot ignore the communication delay. So therefore, we can re-examine this case and put the delay there and looking at the plant control. After the delay, the reactive power order will send to the inverter level, and the inverter level's reactive power will follow the order and influence the voltage. So using that, we can form a control feedback loop. And this guy can really tell us what's happening. And we plotted the root locus. Basically, this one shows that if we increase the gain, you can see increase the voltage regulator gain, we can make the system unstable. And all because of the delay. If you take out delay, the system is always stable. So this case basically tells us this is, we sort of like this aha moment that we capture those kind of final kind of challenge in that case. So with that, we will move forward to think about build a model, mathematical model to capture the full picture. Because the previous one, we only talk about the voltage and the reactive power. We haven't considered the real power. And we have to capture that the real power ramp up, oscillation will happen. Right? Yeah, and yeah, so this time then we have to capture the real power. So the left figure is a simplified model. The right figure is now the with real power effect captured. So the assumption is still is a simplified assumption. The converter is not like EMT. Everything is in detail here. We assume the inverter is just a current source, but we have modeled the outer power control loop into this picture. Now, this model can really tell us all the 3 critical features of the weak grid oscillation observed in the real world. For example, high power makes oscillation worse. Weak grid makes oscillation worse, and the large plant level voltage control makes oscillation worse. Okay, so then we said, that's great. And this one we can continue, in fact, use this one because we found there are some other oscillations. For example, this is another oscillation in real world, 0.1 Hertz oscillation in the right figure. Basically, you can see that oscillation happen when the power ramping up. This is for solar PV plant total about 1,000 megawatt total. And when it ramp up, the real power oscillation happen in the voltage and reactive power. And check the real power measurement. Nothing happened. There's no oscillation. So can we use the previous one to explain this one? And in fact, the answer is yes. Because the previous one, we built the transfer function, everything is mathematical, and we can use delta P versus delta V, derive the transfer function and plot the body plot, which we can see that the real power to voltage really have very small gain at the low frequency. So therefore, the previous model can even explain this one. It's like the oscillation more obvious in voltage reactive power, but not in real power. So last time, I again checked back the ERCOT paper written by Fred Wang, 2011, because he plotted Texas forecast oscillation just the voltage, not the real power. So I was just thinking maybe the real power oscillation really you cannot see it. Right? It's very insignificant. Right? So that's why they plot just the voltage. Right? Okay. So having said this, we want to do the final match is basically we want to redo our oscillation replication study. So this time it's the EMT simulation, MATLAB Simulink, SimScape. In fact, SimScape, like computer simulation. We put the hybrid power plant there, PV and battery plant level control, everything is there. And now we emulate the tripping event. And this time we want just capture that there is oscillation happening, but the power, real power, you will see less oscillation. So here we put the same scale for the real power and reactive power. And then you can see really reactive power have oscillation, but real power you see insignificant oscillation. Yeah, so this is a couple of like iterations. You can see that we're trying to understand various of the critical feature. So with that, I have the concluding remarks is that grid oscillations have various causes. As the first step, I think collecting sufficient information is utterly important. There are lots of critical features like generators, grid influence, real power, reactive power, grid strength, series compensation, shunt compensation, voltage control. And I usually read the NERC report, secret report for multiple times to make sure that I understand each event thoroughly. And then with that, we have this replication and mechanism analysis, which require hands-on computing. Necessary that we have to do experiments, hands-on computing, EMT. And then I think the most important thing is that also we want to connect dots and keep doing iteration, although it takes years to finally understand everything. Thank you.
To our fourth presentation, and now this is going to actually be a tag team between two of our presenters today, Dr. Pengwei Du and Dr. Shruti Rao. Pengwei and Shruti are going to talk about stability impacts of providing frequency response from inverter-based resources in Texas, and this is going to be kind of a precursor and a culmination of a study that ERCOT, GE Energy Consulting, and Hickory Ledge did together to investigate using inverter-based resources for providing frequency response. So looking forward to this discussion. So Pengwei is a supervisor of resource forecasting and analysis with ERCOT, leading the effort of integrating renewable resources into system operations. And he's also a fellow of IET. And Shruti is a senior engineer with GE Energy Consulting and leads our initiatives around development of our positive sequence load flow PSLF program, as well as working on many large system integration analyses, such as what you're going to see today. So please help me welcome Pengwei and Shruti.
Good morning. Thank you, Charlie, and thank you, Jason, and to give me this great opportunity to speak this morning. So all the other panelists, Junior, Dr. Babak, and also Professor Feng, set a good stage for the great forming technology. It's a very promising. It's exactly what we need for the future power grid. But between now and the time when the industry adopts this grid forming inverters in the large scale, we still have a problem we need to solve today. And from the Texas experience, this problem is just becomes more pressing. So today I like to co-present with Shruti from the GE team and to share some thoughts we have about this problem. So this morning, I'm going to walk you through three things: who we are, what are we doing today to meet about 003 local reliability standard requirement, and also the new trend and the problem we're trying to solve. We are one of the interconnections in the North America. Literally, we are electrical island. It means we have to rely our internal resources to balance between the demand and the supply. And this really is a challenge because of the shift in the resource portfolio in the past 20 years. So it is not a surprise. Probably you have seen the similar trend for other regions. And we add more renewable resources. And today we almost have a combined over the 45 gigawatt of the wind and solar together. And this installed capacity will continue to grow. And all those, the wind or solar resources, they are type 3 or type 4 inverters, and they don't contribute to the system inertia. And also they don't provide any frequency response if not curtailed. So we need to think about what is the reliability risk we want to solve for the ERCOT grid. On top of this, we have another dimension of the complexity. We have seen influx of the batteries coming to the ERCOT grid. So today we have about 2,000 megawatt of these batteries. And by the year 2025, so total amount of the batteries could be about this 10,000 megawatt. As the grid reliability risk is changing, we are changing also what type of answer service we are buying and the volume of the answer service we are buying. So next year, we are going to introduce this called the ERCOT Contingency Reserve Service, ECRS, which is a 10 minutes RAM product to help us to solve some RAM issue we are seeing today. But today, this morning, I like to focus on my discussion on the response reserve. Why does this response reserve matter to ERCOT? Because we need to procure certain amount of the response reserve for every seconds. Make sure we protect the ERCOT grid for the greater reliability for loss of the two largest nuclear units, which amounts to 2,800 megawatt. For the planning purpose, we add 100 millihertz as a margin on top of the first stage UFS triggering frequency. So this means we need to buy this response reserve, make sure the frequency will not drop below 59.4 hertz for loss of the two largest nuclear units. The response reserve can come from two different types of resources. The first one is generators. This is controllable load resources. All these batteries, they can provide the gamma type of response. So for any of these resources online, and ERCOT requires them to have this gamma function enabled, and they can provide this kind of a proportional response. Usually they deliver the response within this from the 12 to 16 seconds as the frequency drops. So also we have this faster frequency response from these load resources or these batteries. So for example, if the frequency drops below 59.7 hertz, those resources could be tripped offline with a delay of these 30 cycles. And for the faster frequency response FFR from the batteries, they can be tripped faster within the 15 cycles when the frequency dropped below 59.85 hertz. So we have the combination of these two different resources to provide the response reserve we need. We study how much response we need actually is a function of the system inertia we are going to see. At the lowest inertia level, which is close to the 120 gigawatt seconds, if we don't have any participation of the load resources, ERCOT could need as high as 8,000 megawatt response reserve for those no inertia hours. Fortunately, because we have this, we can take advantage of this faster response from the load resources. We can almost reduce this response reserve by half for those no inertia hours. As this system inertia increase, our response reserve requirement decreases. And you can see in general, we still buy a large amount of response reserve across all the spectrum of these inertia levels. So you can see more reference in this paper. In general, we on average quantity we buy for every hour in year 2022 is about closer to the 2,900 megawatt. Give you some context of the volume of this response reserve. So last year, in year 2021, ERCOT spent almost close to $800 million last year to procure response reserve we need. So really response reserve has a significant impact in terms of both reliability and also economics. This is the reason why we want to make sure we buy the right amount of response reserve and make sure we buy this amount of this reserve to protect the grid reliability. As we continue to add this more inverter-based technologies, our inertia is in the decline trend. And last year and this year, the minimum inertia we have experienced is closer to the 115 gigawatt seconds. So this no inertia indicates we need to buy more response reserve. When we come to these batteries, and those batteries could be very large in size. So in the planning queue, most of these batteries coming to a Texas grid, their primary intention is to provide answer service. So they have a energy duration less than 2 hours. So in California ISO, you may see the longer energy duration because of the capacity credit given the battery, but it is not the case in ERCOT. So also the size of this battery could be very large, between this 200 megawatt and 300 megawatt. As we continue to add more batteries in our system, because of their economics, so load resources is a price taker for the response reserve. But we have seen those batteries, they already took over the market share from the generation resources to provide those response reserve. So during those hot summer days for the past summer, those batteries could provide about 800 megawatt or 900 megawatt for this RSPFR, and the rest of the response reserve obligation is fulfilled by the faster response load resources. And in terms of the percentage, it almost close to 80% or the 90% is because of the economics of the battery advantage over those synchronous machines. We have seen from our operation experience, some of these batteries could fail to deliver this response reserve when we needed them to deliver response reserve because of the variety of the reasons. some of those failures could cause by incorrect logical implementation, and sometimes it could be caused insufficient headroom to provide the responsibility, and sometimes maybe due to the wrong telemeter data for the state of charge. So example you are seeing here, this particular battery was carrying 9.4 megawatt of responsible reserve responsibility, but for this particular event, it delivered 0 megawatt response. So putting those things together, those inverter-based technology, our ERCOT rule allows them to set their government group as one person. It means they can provide up to 100% of their capacity as RS PFR. And some of them may have failed to deliver the response. And also, we have seen ESRs already provide a large share of the RS PFR. So our question is any concern for us if this RS PFR in the future will be concentrated on a few large these areas? Is a concern. So this is the objective of the work we commissioned with the GE consulting team. The project was kicked off last December, and we plan to complete those later this year. So the end result is to help ERCOT to understand from a technology neutral and the broader perspective, not only just for the inverter resources, but for any technology, whether we have reliability reason to create a limit for those batteries or this any technology to provide the RS PFR. Then I will hand over this Shruti.
So as Pengwei mentioned before that, can you hear me? So GE, Hickory Ledge, and ERCOT worked together on this project. Before we go into what we did or the methodology, this was not a planning study. The objective was not to say that you can interconnect X megawatts of battery or whatever your fast PFR resource is at whatever location it may be. It was more a methodology. What I mean by that is ERCOT already has in place some processes for qualification of PFR resources and for procurement of PFR. And what we were looking at was, as you displace synchronous machines that have 5% group with these, say, 1% group and fast PFR resources, does anything need to change in that process? Do you need to do anything extra? And so on and so forth. So as Pengwei said, there are three types of frequency response that they have. First is the primary frequency response. Then they have the fast frequency response, which we have also considered when we were looking at these fast resources. And then there is the discrete acting load, which kicks in at 59.7 hertz. And that is a big chunk of response that really influences the system frequency. So when we were looking at PFR in the course of this work, we were considering synchronous machines. And I say battery, but we really did it. Whatever we did was not really technology specific. As Pengwei mentioned, it was any resource that can provide a fast PFR. As Pengwei also mentioned, the renewable energy was not providing PFR in our studies. So there were a few aspects that we had in mind when we were looking at different setups, different case configurations. As we were replacing synchronous machines with batteries, there were different constraints or reliability risks that we had in mind. The biggest was frequency compliance. By that, we mean that is the nadir acceptable? And as Pengwei said, that Their first stage UFLS acts as 59.3, and ERCOT has a practice of maintaining 100 millihertz margin. So as we are replacing synchronous 5% group synchronous machines with these fast resources, is the nadir still acceptable? Is the frequency response obligation met that ERCOT has to meet? And is the settling frequency within an acceptable range, right? And in addition to that, there are also some other risks such as voltage stability, especially for cases where there was a significant amount of power being shipped from west and far west to the coast. Is there any particular tie line that gets stressed? Is there any system separation concern, any cascading outages concern? Those were the things we were also looking at. And not just frequency compliance in terms of those three metrics, but also is your frequency recovery fast enough, right? If you have oscillations, be it inter-area, be it local, are they damped enough, right? And if you have, say, any overshoot or backlash, and as I said, there's this load response that kicks in at 59.7. That is a huge chunk of response. So what happens if you're just above or below that threshold? How does that affect the frequency? We also looked at the controls issues, like interactions between different BESS. Again, when I'm saying BESS, I'm not, we used the electrical controller model for BESS, the generic model, but the recommendations that we plan to make are not really limited to BESS. So interactions between BESS and synchronous machines. So far, our IBRs were not modeled. So until now, we've not been able to look at BESS and renewable energy interactions, but hopefully in the future, we'll be able to look at that. And also to see if there is any misbehavior, right? Is any limit cycling happening? Is any fault right through getting triggered that it shouldn't, right? So we were looking at those kind of things too. Any system separation. And one of the concerns that I mentioned was they have potentially upcoming large batteries that will want to interconnect that can offer 100% of their rating. So if now you have a single point of failure and you lose this, you have this event, the 2.8 gigawatt generation loss event, and on top of that, you think you're going to get PFR from this huge chunk of resource and it doesn't deliver, then what happens? So these were the kind of considerations that we had in mind. And to Pengwei's point, the low inertia case was the focus of most of our studies, which was roughly 122 gigawatt second. And we did also look at some scenarios for the moderate inertia, about 245 gigawatt second. And that was mainly to consider the granularity question, in the sense, how large can a single resource be such that the system can tolerate its failure also? So this is sort of an n-2 or n-1-1, right? So we looked at different configurations of where was this BESS being placed in the system, what was the size of each BESS, how distributed was it, and we'll look at that in a couple of minutes. Because we were also looking at voltage stability and transient stability, there were different disturbances that we studied, not just the 2.8 gigawatt loss that Pengwei was mentioning, but also the generation loss that is not big enough to trigger, say, that 59, the load response that gets triggered at 59.7, or it's just high to cause that load response to kick in. Is there an overshoot that is acceptable? So those were the considerations that we had in mind. And there are a couple of critical interfaces that deliver power from the west and far west to the coast. What happens when you lose those lines, right? So these were the sort of disturbances that we were looking at. We will talk about sensitivity in a couple of seconds. So based on all these studies that we did, our recommendations were focused on, as you have more of these fast resources replacing and large resources that offer 100% of their rating, displacing your traditional PFR, what are the additional things you need to do? Any additional locational constraints that might come into the picture? Any controls requirement that you might have to place in? How does it change with different inertia levels, so on and so forth, right? So very quickly, the frequency requirement that we were looking at, since this is something that we were focusing. Oh, sorry that the plot didn't come through. That's okay though. So the nadir for ERCOT, as we said, is 59.4. They have the 100 millihertz margin. The plot that should have been there, that is not, is the frequency response for the base case ERCOT, the low inertia case that we got, where we had not changed anything. We had not put in any battery. We did not displace anything. And we wanted to see what that base case looked like and whether the metrics were met. So the frequency response obligation, that is the amount, the megawatts of PFR that you get per 10 millihertz degradation of your settling frequency, what that looked like. I really wish that curve had come up. But anyway, so you see this red curve on the bottom, that's the load, and you see that vertical drop, that's where the discrete load response kicks in. That about 1150 megawatts of load response to that frequency. And take my word for it that the frequency behaved okay. So what system ERCOT has in place right now? And I'm not saying this is the only thing ERCOT has in place, but this is something that really helped us as a guiding when we were working on this project. So ERCOT has a guideline of how much PFR they need to procure versus as a function of the inertia. So at low inertia levels, if there is no LR, how much PFR they need increases with reducing inertia. And also at lower inertia levels, the value of that load response, that discrete load response, is much higher as a ratio of the PFR compared to high inertia levels. So when we were replacing synchronous machines with these fast acting PFR resources, we were essentially equivalent PFR the same, considering the load response, considering the synchronous governors, and considering what we were adding for the batteries. We kept that the same as we proceeded. Throughout all these studies, whatever we replace are continuously acting PFR resources. So our conclusions would not apply to discrete acting PFR resources, but for continuously acting fast frequency response resources. So this is the different sort of broad setups that we were looking at. The leftmost is to ERCOT's question of how large can the battery be, what happens if it's offering 100% of its capability. As a corner case, we put one large giant battery of 2.8 gigawatt near the coast. We are not by any means suggesting that this should be that you install resources of that larger capacity, but we just wanted to see what happens if we put that in there, and how does the system response, what does the frequency compliance look like. Then on the second curve that looks sort of a dumbbell, there are two resources, fast acting resources on the west and far west, and then there are two near the coast. And we in addition to frequency compliance and stability, we also wanted to look at interactions here. A couple of those batteries were close to steam plants to see if there's any torsional interactions. And we were still looking at PSSE. So not that this was a proper torsional interaction study, but just to see what is the impact on the shaft speed of the nearby thermal plant when, say, this nearby battery is shipping a lot of power, say at like an FFR that ramps up very fast. And then we also tried a case where all of these fast resources are out in the west and far west, right? So now there is this concern where a lot of power is being shipped from the west and far west to the coast. How does that stress the system, the voltage? Is there enough voltage support for that power to get shipped from the west to the east? So we were looking at those sort of concerns. Again, interactions, best interactions, best synchronous machine interactions, any system separation issues we were on the lookout for. And then for the fourth column that you see there is granularity, where essentially we plan for, we procure assuming we have these 4 guys providing their PFR, but one of them does not deliver. What happens in that case to the frequency compliance? Is there any limit happening? Is there any tripping happening? And this was not all that we did for granularity. Actually, we ended up doing a lot more. We also tried to see what happens if your load response does not come in, and to sort of see what is the sensitivity of the frequency to failure of PFR as a function of inertia to help ERCOT address some of the questions that they had. And lastly, we got from ERCOT their pipeline planned BESS for the interconnection plan for battery, and we used that to place batteries of the planned sizes. And we did a bunch of sensitivities here. We for instance, saw what is the impact of displaced governor. So depending on where we are displacing the synchronous PFR from, what is the impact of that? What is the impact of speed of response? For instance, for lack of a better word, baseline control configuration for BESS was largely within the range of what 2800 prescribes. The rise time was about 3 seconds. The settling time was slightly faster than what 2800 subscribes. What happens if it is much slower than that? Do you start eating into your 100 millihertz margin? What happens if you're much faster than that, but you have a latency or you have a delay, larger delay between your plant controller and your electrical controller? Do you have risk of oscillations in that case? What happens when the guys that are in the far west and west are acting much faster than the ones who are in the coast? Any interaction issues when you do something like that, right? We also looked at sensitivities for headroom. We looked at inertia. We looked at group, not just 1%, 0.5%, 5%. So we've looked at a bunch of sensitivities for this. And unfortunately, we're not in a place to share the results because we have not wrapped up everything yet. We have to still discuss with our stakeholders, but hopefully next time. I'll hand this back to Pengwei.
Thank you. Thanks, Shruti. I think really what I like to say as a final words is really we need to adopt this grid forming technology fast so we can solve a lot of the problem today we have. Thank you very much.